Hello everyone, welcome to the 17th lecture for the NPTEL course on Computer System Optimization for Machine Learning. Today we will give you a brief recap on whatever we discussed in the last lecture, and then we will continue discussing about Eyeriss V2, which is an extension of Eyeriss V1 which we were discussing in the last lecture. And then we will discuss about DNN pruning. So in the last lecture we talked about the Eyeriss structure, where the main idea was to propose a row stationary data flow. So row stationary data flow is kind of combination of wait stationary as well as output stationary data flow. If you remember, in this row stationary data flow we have 3 by 3 PE in this case, which is performing the convolution of a 3 by 3 kernel on top of a 5 by 5 image, right. So that's why we have these 5 rows, which is denoting this 5 by 5 image. And in this row stationary data flow, the data is flowing in such a way that from each group of PE we are getting one particular output row. That is why it is called row stationary data flow. Now we also discussed the area breakdown of the Eyeriss chip, and most importantly we discussed that although PE array is consuming 78.6% of the total area, which is approximately 80% of the total area, but inside PE array scratchpad takes 60% of the area. So 60% of 80%, which is nothing but 48%. So 48% of the total area is taken by scratchpad. Not only that, we can see that global buffer is taking almost 20% of the area. So 60%, 48% or 50% of the area is taken by the scratchpad, and global buffer is taking another 20% of area. So in total, like approximately 70% of the area is taken by the storage itself or the memory itself, which is the case in any of the DNN or any machine learning accelerator, where memory is probably most critical element in the whole accelerator. Now let us discuss about Eyeriss V2. Eyeriss V2 is a flexible accelerator for emerging DNNs on mobile devices. Now of course we discussed about Eyeriss, where we have this particular structure, we have this PE array, then we have a global buffer, we have bunch of peripheral circuits which is like RLC, decoder and encoder, and then this is interfacing with an off-chip DRAM, right. So this was Eyeriss V1, and of course it implements the row stationary data flow, which is implemented in this 12 by 14 PE array, right. But then what's wrong with the Eyeriss? Let's think about communication perspective. I mean, of course Eyeriss has a good data flow, it has like specific encoder and decoder structure to combat with sparsity in the data, but then if you look closely, this global buffer and then the PE array has lot of communication in between, and then this communication is whenever we say communication, that means global buffer sends all this filter, input feature map, partial sum, etc. So all these type of data, filter, input feature map, partial sum, they are being communicated between the global buffer and the PE array, right. Now it's a huge data communication. So if you calculate, like for AlexNet, it might come up to be like tens of GBs if not more, right. Now that much huge data communication is happening only through one channel. There is, or maybe only one interface. There is only one interface between the global buffer and the PE array. With respect to that the whole communication of every data is happening on that interface itself. So although our although our compute element might be very fast, we have a very good data flow, we have a good data compression technique, but still the communication latency might be the bottleneck, because there is only one single communication channel between the global buffer and the processing element, right. That is why in Eyeriss V2 they have proposed distributed communication. They have proposed a structure where they are distributing the communication. So in Eyeriss V1 we saw that there is only one global buffer or only one global buffer structure and then another PE structure. As I was saying, that between that global buffer and then the PE array, there are multiple communication channel. Not multiple communication channel, between the global buffer and the PE array there is only one interface for communication, which may slow down the whole communication process, and which in turn will hurt the total latency, the end-to-end latency. Now, to address that challenge, in Eyeriss V2, the authors have distributed the communication. In this particular structure, you can see that we do not have no single global buffer or no single PE array. Rather, there is a global cluster of global buffer and then cluster of PE array, which are or there are like group of global buffer, group of PE array, and then there are multiple groups of all these global buffer and PE structure, and all these groups are connected with this 2D mesh NOC, which we discussed when we were discussing DARIA now, right. Now, if we go inside this global buffer cluster or the PE cluster, we can see, or if we just see the top level structure, we will see that, as I was saying, that there are global buffer cluster and PE cluster, and all these clusters are connected to this router cluster. This router cluster is forming this 2D mesh network. Now, furthermore, all these clusters are talking with external memory, which was present in Eyeriss V1 also, where there was a dedicated DRAM, right. Now, if we look inside this router cluster and global buffer cluster as well as the PE cluster, we will see that there is in the global buffer cluster there are SRAM banks to hold the input activation as well as a separate SRAM bank to hold the partial sum, right. And then in the PE in the router cluster, we have a separate router cluster for partial sum, a separate router cluster for weights, and then a separate router cluster for P sum as well as the input activation. So, as you can see, for different type of data structure or for different type of data, when I say different type of data, I mean the input activation, partial sum, weights, etc. You can see that for different type of data, there are dedicated SRAM bank, there are dedicated storage as well as there are dedicated router, right. And if we have dedicated storage also, if we have dedicated routers, then definitely there will be less conflict, there will be less congestion, and the latency will be lower, the end-to-end performance will be higher. Now, going back to PE cluster, PE cluster has PE cluster is similar to the PE cluster which we saw in Eyeriss V1, which is nothing but some x by y PE array. But most importantly, in Eyeriss V2, the authors have distributed the communication. In V1, we saw there is only one PE array and then only one global buffer. There is a single interface between the global buffer and the PE array. Since the single interface is used by different types of data like input activation, partial sum as well as weights, the communication will be slower in Eyeriss V1. Now, in Eyeriss V2, there are global buffer cluster, PE cluster and router clusters. All these global buffer cluster and the PE clusters are connected through the router cluster. Inside global buffer cluster, there are separate SRAM bank for input activation as well as partial sum. So, there are no conflict. So, there are separate buffers or separate memory for input activation and partial sum. Now, in the router cluster, there are separate router cluster for the separate group of router for partial sum, weights as well as input activation. So, again, whenever the partial sums needs to be routed, they will go to the partial sum router. Whenever weights needs to be routed, they will go to the weight router. Now, finally, we have PE cluster which is similar to the Eyeriss V1, where we have multiple of these PEs. Now, one biggest advantage of this kind of distributed communication is one can enable reconfigurable computing. When we say reconfigurable computing, we mean that the hardware will be fixed, but depending on the data flow, depending on the workload, the communication or the how or the fact how the data is flowing will be different. So, that is the reconfigurable structure. Now, going back or taking a little step back, there are different NOC designs, okay, till the paper was published. So, there is something called unicast network, there is something called 1D systolic network, 1D multicast network, then broadcast network. So, when we say unicast network, that means this global buffer will send all the values to first PE. The first PE will keep some value and then send the rest to the second PE, and then the second PE will send the values to third PE, and so on and so forth. That is the unicast network. Now, systolic network, we already saw the systolic networks when we were discussing the systolic array. We discussed that in systolic array the data flow in a specific manner. In multicast network, the global buffer sends some data which is communicated, the same data is communicated to all the P, that is the multicast network. And finally, the broadcast network is global buffer will send one single data and that single data is communicated to all the P's, right. So, these are the different like data flow or the different types of NOC. Now, if you see, if we go to the right hand side, if we go from left to right, then it reuses, there is a high spatial reuse, but the bandwidth is very low. When we say bandwidth is very low, that means the less amount of data is being transferred, but then same data is being reused across multiple P's. For an example, here only one data is transferred from global buffer to all the P's. So, the amount of data transfer is less, but then the same data is getting used across all the P's. Now, in contrast, if we go from right to left, we will see that the bandwidth is high, the amount of data transfer is high, but then each of the PE is getting separate data. So, there is less spatial reuse, right. Now, in Eyeriss, so of course, I mean both are good or bad, like low bandwidth, high spatial reuse is bad because the bandwidth is low. On the other hand, high bandwidth, low spatial reuse is also bad because the reuse is bad. When we say reuse is bad, that means the same data may need to be computed again and again, right. Now, in Eyeriss V2 architecture, the authors propose something called reconfigurable NOC, where depending on the data flow, depending on the need for communication, they can modify the data flow. Specifically, if you see that, I mean if you think that maybe weights has to be broadcasted, right, or maybe the partial sum needs to be unicasted, right. So, if it needs unicasting, then it can switch to different set of global buffer or different set of routers, so that the corresponding data flow can be activated. Now, again, let us say if something has to be broadcasted, then again the network will be automatically switched to different global buffer cluster as well as router clusters, so that the data can be broadcasted. So, this is a reconfigurable architecture where depending on the workload, the data flow, the data communication is different. So, there are provision for all these data flows or all these types of data communication pattern. Now, as per the need of the workload, the corresponding data communication pattern is activated, because there are different types of router cluster as well as global buffer cluster, right. So, if you remember in the previous slide, I was showing that some router is responsible to route the PSUM, some router is responsible for the weights and so on and so forth. Since we have different router as well as different memory or SRAM bank for different types of data, that is why this kind of reconfigurable NOC or the reconfigurable data flow can be enabled in the hardware. Now, with that, let us start discussing about DNN pruning. So, DNN pruning is a vast topic. So, most likely in next one if not two lectures, we will discuss about DNN pruning. So, there are multiple topics in DNN pruning. So, first we will discuss why do we need to perform DNN pruning, the need for smaller models, and then we will discuss how to select which parameter to prune. So, remember DNNs have many parameters. So, for an example, in AlexNet there were probably hundreds of millions of parameters, right. Parameters means weights. And then we will finally develop a recipe for DNN pruning. When we say recipe, that means it is a generalized technique or generalized method to perform DNN pruning. After that, we will see that okay, I mean DNN pruning, probably you have heard this term pruning many times, where while it is very effective to reduce the hardware footprint or to improve the performance of the DNN, but then there are multiple problems. The main issue with DNN pruning is to how to regain or how to get original accuracy even after pruning. And then finally, we will discuss the role of underlying hardware on DNN pruning. So, we will see what is the effect of computer systems or how to make this DNN pruning effective in terms of underlying hardware. So, again, I mean let us have a quick recap of what discussing for many lectures. We need smaller models. I mean although we have seen that from Elinet to AlexNet to VGG to ResNet and DenseNet, the accuracy of ImageNet dataset is improving, but at the same time the number of parameters is increasing drastically. and whenever we have this higher number of parameter, then we have, I mean, the execution time will be higher, the user experience will not be so good, right. Now another important thing is, I mean, whenever we have this large neural network, many a time they are over parameterized. It might be the case that not all the parameters of the neural network are actually useful. And then again, if we deploy, let's say on the edge devices, let's say on our phone, the cost is higher, because remember, whenever, let's say in our phone there is a ResNet network deployed to do some image processing task which is on the images which is captured by your phone camera, right. Now, I mean, as you have already seen that ResNet has like very high number of parameters, right. Now whenever we need to execute that ResNet, or let's say whenever we are taking a photo through your phone, we need to execute that ResNet, right, and then to execute that ResNet will take some power, some latency. Now if it takes large amount of power, then your phone battery will get drained very soon, correct. So that's why there is a high cost of sustained inference. And then again, there might be the case that I mean, some DNNs we may be unable to run some DNNs on edge devices, because the inference time is very high or the memory requirement is very high. And I mean, I already discussed about energy consumption, right. So this particular figure is showing the current state of the model size from 2017 to 2021. So if you see the model sizes, like let's say the state of the art model which like Google started with transformer, which was merely 0.05 billion, which is like 50 million, right. The number of parameters was 50 million, but the GPT-3 by OpenAI has like 170 billion, and this is the story of like 2021, like today is 2026, we are talking about trillion parameter models, correct. So as you can see, I mean, the number of parameters in the model is like growing exponentially over like past decade or whatever, right. And as I was saying, that many of the parameters, many of the weights are actually useless, correct. So that's why we need to find the useless weights or useless parameters, and then if we can prune so that the accuracy, the resultant accuracy doesn't change, right. So that's the main goal of DNN pruning. Now the basic technique of DNN pruning is to somehow create a compressed models with faster execution times and without losing the accuracy much. So there are techniques called knowledge distillation, where a smaller, which is known as student model, is made to learn from a bigger, which is known as teacher model. But then this knowledge distillation suffers from the drawback of having to define a completely new model and train that model from scratch. So many a time we might not have access to the data set, or we might not have enough computational power to train a model, to train even a small student model from scratch. So that's why this knowledge distillation is not so popular technique when it comes to model compression. Now a better approach is to compress an existing model without training any new model from scratch. That's nothing but DNN pruning. Now let's take some basic example. So this particular slide is showing the overview of DNN pruning, where we have multi-layer, where we are showing a multi-layer perceptron with just two layers, right. There are two layers of weights, correct. Now again, I mean, any neural network or any multi-layer perceptron weights can be represented as matrices. So let's say this is the initial matrix where we have all the numbers present. So different heat map is showing the absolute value of those numbers, absolute value of those weights, right. Now we can remove some edges to get this pruned network. If we remove some edges, then as you can see that some of the absolute value will be 0, correct. So that's the DNN pruning. We just remove some edges or remove some weights so that the resultant matrix is more sparse, so there are more zeros, right. That's one way of DNN pruning. Another way is we can remove node. So in this particular example, we have this input network and then we have removed this node. So you can see that remove is no longer there. We also removed this particular node, right. So this particular node is no longer there in the pruned network. Now if we remove nodes, then the whole row in the weight matrix will be 0, correct. So, we will remove the entire row of the weight matrix if we remove particular row. So, that is another way of DNN pruning, correct. Now, in case of convolutional layer, there can be multiple pruning granularity in DNNs. So, first granularity can be fine grained, where we can prune the individual weights. So, for an example, let us say we have this particular case. So, let us name this case 1, 2, then 3 and then 4. In case 1, in all the cases we have considered 2 filters, each filter has 3 channels. Okay. Now, so this is the filter 1 and this is filter 2, this is channel 1, sorry, channel 2 and channel 3, 2 filters, 3 channels, right. Now, the most fine grained pruning granularity is to remove the individual weights. So, you can see that some of the weight values are 0, that is why those positions are white. So, those values are removed, right. Now, instead we can also do a vector level pruning, where we can remove one rows from one particular channel of one particular filter. So, that is another granularity of DNN pruning. Now, kernel level, we can remove the entire kernel of shape H by W from the DNN, right. And then finally, we have filter level, where one particular filter has been removed. So, that is why you can see that the whole filter is removed here, and that is why we have all zeros for those weights. Now, as we go from left to right, it is called so in the left side, these are the examples of unstructured pruning. In the right side, these are the examples of structured pruning. As we go from left to right, we can say the pruning is becoming from unstructured to structured, right. Why structured? Because if we take the example of the example which we are discussing in case 4, where we remove the entire filter, right, that is the most structured way of pruning. But then if we remove if we remove individual weights, like in the case like in the example shown in case 1, there the pruning is more unstructured. We are cherry picking the weights and then removing them, correct. Now, there are advantages of this and as well as disadvantages of both unstructured and structured pruning. In unstructured pruning, we have finer control over selecting elements to prune, right. I mean, we as I told, we are cherry picking in this case. So, you can pick any individual weight and then make them 0, right. It will provide a better sparsity to accuracy ratio, that is a smaller network with higher accuracy. We may end up pruning like 90% of the weight still without changing the accuracy, but then it is difficult to implement. So, if you remember, when we talked about a naive 7 layer for loop implementation of convolutional neural network, you remember that there are for loops, right. There are a series of for loops and then we implemented the CNN layer, correct. But now, if we have this unstructured pruning, where we are doing fine grained pruning, you have to remember the position of the weights and then make them 0. So, you may or may write that 7 layer for loop, but then additionally you have to implement something, you have to access all those particular weights individually, correct. So, that is why it is difficult to implement. But then if you talk about this final case, the case 4, or I think we wrote 4 not D, that is the most structured pruning example, right, where we just removed one particular filter, right. Now, if we removed one particular filter, then again if you think about the implementation, you will understand that we just need to change the loop boundary. So, if the filter size, if the number of filter was m in the previous case, then we were writing for I is equal to 0, I less than m. Now, if we remove 2 filters, then the number of filter will be just m minus 2. So, you just need to modify the loop boundaries. That is why structured pruning is more easier to implement. But again, in structured pruning, we have less control over selecting elements to prune, because we cannot cherry pick the element. If we have to prune, in this case, let us say in the 4th case, we have to prune one particular filter, otherwise we do not prune, right. Now, that is why it has relatively less sparsity to accuracy ratio. So, it may be the case that beyond 20% pruning we may lose the accuracy. We will see some more example, but it is easier to implement, right, because as I was just saying that we can just change the loop boundaries to implement the structured pruning. Now let us see the mathematical definition of pruning, right. So DNN pruning can be defined as arg mean of P L of WP comma D such that phi of WP less equals to C. Let us try to understand what this mathematical expression is trying to say. Here L is the loss or objective function of the DNN. So you can think that it's a measure of accuracy, right. And then D is the target data set. Let us say we are talking about MNIST or ImageNet, so those are the target data set. W is the original weights and WP which belongs to W is a subset of weights remaining after the pruning, and phi is some function which maps the network to some constraint C such as inference time, flops, memory, etc. So C is some hardware performance metric. So basically this particular expression is trying to say that through DNN pruning we will prune the network in such a way that the prune network has some good hardware performance. At the same time we will take the network which has lowest loss on the same data set. So it might be the case that let us say if we say that we will prune the network 20%, let us say that is our target. Now there can be many 20% prune network which satisfies this phi WP less than C, which satisfies some number of flops or some inference time, right. But out of those networks, out of those prune networks which is pruned by 20% and then satisfying the hardware performance, out of all those networks we need to select the network which incurs least loss on the same data set. That is the target of pruning. Basically we need to prune so that we do not lose in accuracy, as well as the hardware performance has meaningful gain over the baseline network or the unpruned network. So that is the mathematical definition of DNN pruning. Now the biggest question is which parameters to prune. Of course we need to select the less important parameters to prune, that is no brainer. We need to prune or we need to drop the parameters which are not so useful for DNN, but then how can we choose those parameters? The general technique is to define a saliency term which can map each parameter to some importance score. So we can say that if there are like 100 million parameter in some DNN, we can assign some score to each of the parameter, and then the importance score can be the loss in performance when removing that particular parameter. After that we can just remove the lowest salient parameters from the network. So basically if we have, let us say AlexNet has 138 million parameter, if I am not very wrong, it has 138 million parameter, then we can assign some cost function or some loss function to all these 138 million parameter values, right. We can say that, let us say third parameter, if we remove the accuracy is degrading by 10%, something like that. So each of the parameter has to be associated with a saliency term. So that is loss or accuracy, whatever is the saliency term, and then if we can do that, after that we can remove the lowest salient parameters from the network. So that is the general rule of DNN pruning. Now let us take few example of DNN pruning. So first one is magnitude based pruning. So let us say we just have one layer of perceptron or just one perceptron where 3 weights are coming. The weights are nothing but 10 minus 8 and then 0.1, and then this, since this is a just a perceptron, we can compute this perceptron as summation of Wi xi plus the bias term, and then on top of that we have to apply the nonlinear function. Now if you can afford to remove one weight parameter, which one should we remove? Of course, I mean if we just want to remove based on the weights, we will remove the weight which has the lowest value, right. So that is nothing but, if we do that, we are saying that our technique prunes DNN where the importance of the parameter is given, or the importance of a parameter is proportional to the absolute value of the weight. So that is a magnitude based pruning. but that this particular case might not be good, because again maybe the W2 has least weight, but it might be the case the value x2 is always very high with respect to x0 and x1, right. So that is why we cannot remove W2, but again if we just have visibility to weights, then we can devise a technique where the importance of the weights is nothing but the absolute value of the weight, and then we can prune the weight which has the least absolute value. So that is a magnitude based pruning. Now in terms of filter, yes, we can remove the parameters whose absolute value is closer to 0. If we have like convolutional neural network where we have multiple filter, there if we want to do the element wise pruning, then we just need to take the absolute value of the filter weights. After that we can just get the importance, or we can say that whichever weights or whichever element has higher absolute value, that has higher importance. So in this case you can see that 3 and 5 is retained, where 1 and 2 is pruned, right. So that is the magnitude based pruning for element wise pruning, right. Again if we have right, like let us say if we are doing filter based pruning. So sorry, this is not element wise pruning, this is filter based pruning. Filter wise pruning, let us say we have two filter 10 minus 5 3 14 and then 1 minus 5 3 and minus 2. Now we can just see if we want to if we want to do filter wise pruning, we can just see what is the sum of the absolute value of all the weights, and then we can prune the filter which has lower sum of absolute value. So in this case the second filter has lower sum of absolute values, so we can just prune the network, right. So with that, let us end this lecture. In the next lecture also we will continue discussing with DNN pruning, and we will see what are the hardware implication of the DNN pruning. Thank you for your patience and consideration.